The universe does not rush. It expands in silence, vast, cold, and patient beyond imagination. We are drifting through that silence on a small blue world suspended inside a space so empty it defies our intuition. When you look up at night, the sky seems full, stars scattered like grains of salt on black velvet. But the truth is different. Most of the cosmos is not stars, not galaxies, not even dark matter. It is absence, and within that absence, we live in one of the greatest hollows ever discovered. A cosmic valley so wide that light needs nearly 1 billion years to cross from one side to the other. Astronomers call it a supervoid, and the one surrounding us bears the name of its discoverers, Keenan, Barger, and Cowie, the KBC Void. This story begins not with mystery for mystery's sake, but with a question that has haunted modern cosmology for decades. It is a question of measurement, of speed, of distance, of time itself. How fast is the universe expanding? Two answers exist. Both are supported by evidence. Both cannot be true at once. That contradiction, the Hubble tension, is one of the deepest puzzles in science. And to solve it, we may need to accept that our cosmic neighborhood is playing tricks on us. Think of the universe as a vast ocean. Galaxies are ships scattered across its surface, carried apart by the swelling tide of space. From where we float, we try to measure how quickly that tide rises, how fast the cosmos stretches. Yet if our ship sits in an unusual current, the waves beneath us distort what we see. We might think the entire ocean is speeding up when, in truth, it's only the local water rushing beneath our keel. That is the essence of the void hypothesis. We live inside a giant underdense region, and this cosmic geography makes the universe appear to expand faster than it truly does. A sky that wouldn't fit the model. At first, no one believed such a thing could matter. The standard model of cosmology, LCDM, lambda cold dark matter, is a triumph of physics. It describes the entire cosmic story with just a few parameters: matter density, dark energy, and the Hubble constant, which tells us how rapidly galaxies recede from one another today. According to this model, the universe should be smooth when viewed on scales larger than a few 100 million light-years. Any small clumps or voids would average out. But reality, as it often does, refused to be tidy. In 2013, a team mapping galaxies within 1 billion light-years found a surprising pattern. Where theory predicted an even spread of cosmic structure, their catalog showed an emptiness, a thinning of galaxies in nearly every direction around our own. Not a small hole, but a gulf. Imagine a soap bubble so large that it contains tens of thousands of galaxy clusters along its walls, while its interior stretches nearly empty for hundreds of millions of light years. That bubble, they realized, was home. The KBC Void is not an absolute vacuum. It is simply less dense, containing perhaps 20% fewer galaxies, stars, and dark matter than the cosmic average. But in the delicate mathematics of expansion, that deficit changes everything. Where matter is scarce, gravity's pull weakens. Space itself expands a little faster. Edges of the void tug outward, while the center, our region, drifts with the outflow like dust caught in a gentle wind. To observers living inside, galaxies seem to be receding quicker than they truly are. And so, when we measure the Hubble constant locally, we find a higher number than the one derived from the early universe. The difference is not an error in our telescopes. It is a mirror held up to our location. Sometimes the map is honest. It's our place upon it that lies. A conflict written in numbers. The Hubble constant should be simple. It tells us how fast galaxies move apart, their velocity divided by distance. In the 1920s, Edwin Hubble discovered this relationship using the light of distant galaxies. For nearly a century, astronomers have refined that measurement, comparing standard candles like Cepheid variables and type Ia supernovae to determine precise distances. Recently, local measurements using nearby galaxies and the light of exploding stars converge around 73 km per second per megaparsec. Meanwhile, data from the early universe, the cosmic microwave background mapped by the Planck satellite, implies a slower expansion, around 67 km per second per megaparsec. The numbers differ by only a few kilometers, yet in cosmology that gap is immense. It exceeds the margin of error by many standard deviations, enough to suggest that something fundamental is missing. Is dark energy changing over time? Is gravity not what we think it is? Or are we simply seeing the universe from a skewed vantage point? Enter the void. If we are floating in a vast underdensity, then our local galaxies are carried outward faster than the universal average. Their additional motion adds to the redshift we measure, stretching their light beyond what cosmic expansion alone would produce. Our calculations, unaware of the local current, interpret this extra push as a faster global expansion. In short, we're inside the wrong laboratory. Astronomers call this effect peculiar velocity bias. Inside a void, peculiar velocities, the local motions due to gravity, no longer cancel out statistically. Instead, they line up, all pointing outward. The result is a systematic inflation of the measured Hubble constant. Simulations show that a void with the size and depth of the KBC region could boost the apparent expansion by roughly the observed amount. That coincidence is too precise to ignore. Gravity's strange direction. Gravity always attracts, yet inside a void, its choreography changes. Imagine standing in a shallow valley, ringed by mountains. Gravity pulls you toward the slopes, outward from the valley's center. The same geometry plays out across hundreds of millions of light years. Mass, concentrated in the surrounding cosmic filaments, exerts a collective pull on everything inside the void, drawing galaxies away from the center toward the dense walls. From within, this feels like repulsion, as though the center itself pushes outward. But it is simply the universe's landscape obeying its own shape. Astronomers can see this flow directly. By measuring redshifts and distances of galaxies near known voids, they map velocity fields. The pattern is unmistakable. Galaxies at void centers move outward faster than expected, while those near the edges slow as they approach denser regions. Our own galaxy participates in this exodus. The Milky Way, along with its neighbors in the local group, drifts at hundreds of kilometers per second relative to the cosmic background, partly due to the gravitational imbalance created by the nearby local void and the larger KBC Supervoid enveloping it. We are, quite literally, being pulled by emptiness. Perhaps emptiness is never truly empty. Perhaps it is simply the quiet side of gravity's song. Yet the age that wouldn't agree. If our measurements of expansion are biased, then everything derived from them falters. The age of the universe, for instance, depends on how quickly it grows. Using the slower early universe value gives an age of about 13.8 billion years. Using the faster local value shortens that to 12.7 billion. The difference is not trivial. Some of the oldest stars, ancient red giants in globular clusters, appear to be around 13 billion years old. They cannot be older than the universe itself. Yet the local Hubble constant would make them so. Either stellar physics is wrong or our local measurement is misleading. The void hypothesis resolves this quietly. Both measurements can be right in their own contexts. The early universe value reflects the true global expansion, unaffected by local structure. The local value, taken from within our underdense region, describes only our immediate cosmic neighborhood. Each tells the truth about the world it sees. Truth, after all, is local to the observer. The universe, patient as always, allows both to exist. Dark energy and the mirror of the void. Dark energy, that invisible pressure driving the acceleration of the cosmos, makes up about 68% of all that exists. Its properties are inferred from how expansion behaves. If our local measurement is skewed, our understanding of dark energy may be too. A higher expansion rate implies a stronger acceleration, and thus a different dark energy density. Some researchers suggested that dark energy might evolve with time, changing its strength as the universe ages. Others even proposed new physics, perhaps an additional burst of expansion in the early universe to reconcile the numbers. But if the void explanation holds, those exotic solutions may be unnecessary. The apparent extra acceleration could simply be the perspective of observers living in a fast-expanding bubble. From inside, space seems to rush outward more quickly. From outside, the overall universe behaves exactly as expected. The cosmos does not owe us a privileged view. It offers only what our coordinates allow. The deeper we look into space, the more clearly we see ourselves, tiny, biased, but aware. Doubt among the stars. Not all scientists accept the void solution. Skepticism is the heartbeat of science. Critics argue that supervoids as large as the KBC should be exceedingly rare in standard cosmology. Finding ourselves inside one, just as we develop the tools to notice, seems suspiciously convenient. Others contend that even such a vast underdensity cannot produce the full magnitude of the Hubble tension. Perhaps part of the discrepancy comes from unrecognized systematic errors, dust-dimming distant supernovae, or subtle calibration issues with Cephid stars. Each proposed fix peels back another layer, yet the puzzle persists. For now, the KBC void remains both a plausible explanation and an unsettling coincidence. If it is real, and evidence mounts that it is, then the cosmological principle, the idea that no place is special, must bend a little. Not break, but bend, enough to admit that our location influences what we observe. This is not arrogance, it is humility written on a cosmic scale. We are not the center of everything. We are simply at the center of our own small hollow, peering outward through thinner air. Beyond that hollow lie the crowded walls of the cosmic web, filaments of galaxies and clusters glowing like veins of light through stone. In the next breath of our journey, we'll trace how those walls formed, how voids breathe, and how even emptiness has structure. Beyond the silence of our cosmic hollow, the universe thickens. Galaxies gather along invisible threads, weaving the grand lattice we call the cosmic web. These filaments are not random, they are the bones of creation. Between them lie the voids, vast pockets of low density that stretch like dark lungs through the body of the universe. To understand the KBC void, we must first understand how such emptiness comes to exist at all. At the dawn of time, the universe was almost perfectly smooth. Tiny ripples in the density of matter, born from quantum fluctuations in the earliest moments after the Big Bang, were the seeds of all future structure. Some regions were slightly denser than others by a fraction of a percent. Over billions of years, gravity amplified those differences. Dense regions attracted more matter and grew into galaxies, clusters, and filaments. Sparse regions lost matter to their neighbors and became the voids. What began as whispers in the quantum foam of the infant cosmos grew into the architecture of everything we see today. And our home, the Milky Way, happens to rest in one of those underdense troughs, a valley surrounded by distant ridges of clustered galaxies. Voids are not completely empty. They contain faint threads of gas, scattered dwarf galaxies, and the ever-present dark matter that makes up most of the universe's mass. But compared to the crowded walls that frame them, they are deserts. Gravity inside these regions acts like a soft breath, pushing matter outward rather than pulling it inward. The galaxies that remain drift slowly toward the edges, leaving the center ever more hollow. If you could see this structure from far above, it would look like a sponge, immense cavities surrounded by glowing walls. Our void is one of the largest bubbles in this cosmic foam. Its diameter is nearly 1 billion light-years. To cross from one side to the other at the speed of light would take longer than the age of multicellular life on Earth. And all the while, space itself continues to stretch, widening the gulf around us. Within these dark volumes, the laws of physics stay the same, but their balance shifts. In crowded clusters, gravity dominates. In voids, dark energy, the mysterious pressure that accelerates cosmic expansion, holds greater sway. This makes voids natural laboratories for testing how the universe's hidden forces behave. When astronomers watch the edges of these hollows expand and evolve, they glimpse dark energy at work with fewer distractions. Where matter is scarce, the truth of space becomes easier to read. The KBC void, in this sense, is a gift. It offers a clearer view of cosmic acceleration precisely because it removes so much clutter. But it also plays tricks on our perception. Living inside a faster expanding region makes the entire universe seem to rush away more rapidly than it does from denser neighborhoods. Our measurements, taken without accounting for this effect, whisper the wrong story. They tell us the universe is younger and more restless than it truly is. The numbers, precise though they seem, are tinted by geography. And yet, until recently, we did not realize we lived in a place where geometry itself could fool us. For generations, astronomers assumed that on scales this vast location did not matter. The principle was simple and comforting. The universe is homogeneous and isotropic. No place is special, no observer is privileged. It was an elegant extension of Copernicus's idea that Earth is not the center of anything. But then, the data began to argue. Large galaxy surveys mapping tens of thousands of distant systems revealed patterns that violated the neat simplicity we expected. Some regions, like the Sloan Great Wall and the Hercules Corona Borealis supercluster, contained astonishing concentrations of galaxies. Others were nearly empty. The cosmic web was not smooth at all. It was froth, dense walls enclosing immense voids. On average, those voids occupy about 90% of the universe's total volume. Most of space, it turns out, is absence. Our own position within that absence makes every measurement we take slightly biased. Imagine trying to judge the weather of an entire planet while standing in the calm eye of a hurricane. From your perspective, the winds appear gentle. But step outside the eye, and chaos reigns. In cosmology, the reverse happens. We live in a region expanding faster than average, so the storm of cosmic growth seems fiercer than it is. This is not a mistake in instruments or equations. It is the universe reminding us that perspective is a physical thing. Every observation carries the fingerprint of where it was made. Astronomers test this idea by studying how galaxies move relative to the cosmic microwave background, the faint radiation left over from the Big Bang. Our motion through that background creates a tiny temperature dip in one direction and a rise in the opposite, a signature known as the CMB dipole. By combining these measurements with galaxy redshift maps, scientists can trace the flow of matter around us. The result shows a gentle but definite outflow from the region we inhabit, consistent with being near the center of a large underdensity. In other words, the KBC Void is not just a theory written on paper. Its fingerprint appears in the motion of galaxies and the faint echo of the early universe. Our galaxy itself is drifting, carried along by this invisible current. Part of our velocity, about 600 kilometers per second, is directed away from the local void center. We are passengers on a slow, grand tide, moving not because of propulsion, but because of imbalance. All around us, the universe breathes, and we are part of that breath. When cosmologists simulate such structures, they find that voids naturally arise in the evolution of the universe. But the size of the KBC void pushes the upper limit of what standard models predict. It is as if we happen to be born in one of the rarest environments possible. Some researchers find that coincidence troubling. Others see it as a simple statistical quirk, no stranger than being born on one particular planet among billions. Yet even those who doubt the void's full explanatory power admit that local underdensities must exist and must influence our observations. The question is not whether the void matters, but how much. Observations continue to refine the answer. When scientists measure the Hubble constant using galaxies within 200 megaparsecs, all inside the KBC region, they obtain the higher value. When they extend their measurements beyond that distance, the rate slowly declines, approaching the lower value from the cosmic microwave background. This gradient is exactly what the void model predicts. Space itself is giving us clues, and they all point toward the same quiet truth. Our corner of the universe is different. Somewhere far beyond the edge of this underdense expanse, the cosmic average resumes. There, galaxies crowd together more tightly. There, expansion proceeds a little slower. And if an astronomer were measuring from that vantage point, they would find a different Hubble constant, one that fits neatly with the early universe data. Their universe would seem calmer, older, and perhaps more patient than ours. Perspective, once again, writes reality. It is humbling to think that the grand equations describing the cosmos depend on something as provincial as our address. But science grows by surrendering arrogance. Each discovery that displaces us from the center of the solar system, from the center of the galaxy, from the center of the universe, has deepened our understanding, not diminished it. Perhaps finding ourselves in a cosmic void is the next step in that long tradition of humility. And still, even within emptiness, beauty persists. The few galaxies that inhabit these voids are unlike their bustling cousins in clusters. They evolve slowly, undisturbed by collisions. Their shapes are delicate, their gas reservoirs vast, their stars young. They are the hermits of the universe, quiet, luminous, and rare. To drift among them would be to travel through silence itself. Light from one to the next would take millions of years. Between them lies only dark matter and the whisper of cosmic microwave background photons streaming endlessly outward. Yet that silence is not loneliness, it is clarity. It is the peace of a universe that does not need to be full to be magnificent. As our instruments improve and our maps grow sharper, the outlines of our void become more precise. We can now trace its boundary where galaxy counts rise again, marking the transition into denser filaments. The KBC Void spans roughly 1 billion light-years in diameter, centered a few hundred million light-years from us in the direction of the constellation Draco. Its shape is not perfectly spherical, no void is. It stretches and warps, molded by the surrounding web of matter. But its overall presence is unmistakable, and with every new observation, the case strengthens. The local universe truly is lighter, thinner, and faster than the cosmic average. It is our celestial desert, and like all deserts, it shapes the travelers who cross it. In the stillness of this emptiness, we find not despair, but perspective. The void does not isolate us. It teaches us the scale of humility required to measure the infinite. It reminds us that every number we calculate, every law we write, carries the imprint of the sand beneath our feet. Our task is not to escape that bias, but to understand it, to map the mirage and read its reflection. For in doing so, we learn that the universe is not lying to us. It is simply speaking through distance, through density, through time. And we, the listeners, are finally learning to hear. Light is the oldest traveler. It crosses the universe without complaint, bearing silent reports from places that no longer exist. Every photon is a messenger carrying two pieces of information, its color and its time of departure. When it reaches us, we reconstruct entire histories from its faded memory. But light is also sensitive. It bends, stretches, and tires as it journeys through the universe's uneven landscape. Between the crowded ridges of the cosmic web and the great hollows in between, space itself is not uniform. It is warped by gravity and stretched by expansion. To move through it is to climb invisible hills and descend unseen valleys. And because energy cannot remain constant across those slopes, light changes as it passes. When a photon leaves a galaxy embedded in a dense cluster, it must climb out of a deep gravitational well. In doing so, it loses a little energy. Its wavelength lengthens, and we observe a redshift. But when that same photon travels into a vast underdensity like the KBC Void, the opposite occurs. There, gravity is weaker, space expands faster, and the photon's path is subtly altered. By the time it reaches us, the light carries both the mark of cosmic expansion and the signature of the landscape it crossed. To the human eye, these changes are invisible. To the instruments of modern astronomy, they are profound. When cosmologists analyze the cosmic microwave background, the faint afterglow of the Big Bang, they find tiny temperature variations scattered across the sky. Some are imprints of primordial sound waves frozen in time. Others are newer scars created as photons from that early light crossed the developing structure of the universe. Voids, superclusters, and filaments, Each imprint their own minute distortions. This effect is known as the integrated Sachs-Wolf phenomenon. In an accelerating universe, photons passing through large underdensities lose slightly more energy than they gain, leaving a cold spot behind them. When scientists stack images of known voids and compare them with microwave background maps, a faint but consistent pattern emerges. Voids correlate with cooler regions. The universe's earliest light, it seems, dimmed a little as it passed through the nothingness. Our own supervoid contributes to that pattern. In the direction of the constellation, Eridanus lies a mysterious cold patch in the cosmic microwave background, an area a few degrees wide that appears several tens of microkelvin colder than its surroundings. Some researchers suspect that part of this cold spot may be caused by a vast underdensity along that line of sight. Whether or not it connects directly to the KBC Void, it shows how even emptiness leaves fingerprints on ancient light. Photons also change direction when they encounter variations in density. Gravitational lensing, the bending of light by mass, usually magnifies distant galaxies when their light passes near clusters. Inside voids, the opposite happens. Because there is less matter to curve space, light rays diverge, slightly. Distant objects appear fainter and smaller than expected. The absence of mass acts as a negative lens. Astronomers now use this subtle defocusing to map voids directly. By analyzing how background galaxies are distorted, they can trace the three-dimensional shape of the invisible hollows in between. Every void casts a delicate shadow on the light behind it, a darkness made not by obstruction, but by lack. This behavior of light is central to the Hubble tension. When we measure the redshift of a galaxy, we assume that the shift arises only from expansion and the galaxy's own local motion. But photons have also traveled through regions of differing density on their way to us. Each crossing slightly alters their energy, adding or subtracting tiny amounts of redshift that accumulate over billions of years. If we live inside a large underdensity, the photons arriving from outside have passed through a region of faster-than-average expansion near their destination. They are stretched just a bit more than expected. Add that up across many sources, and the inferred expansion rate rises, another echo of the void's influence. It is humbling to realize that light, the very thing we trust to tell us the truth, can be persuaded by space itself to tell a slightly different story. The cosmos is not deceiving us, it is simply reminding us that every measurement is a conversation between traveler and terrain. In laboratories on Earth, light obeys with perfect consistency. But across a billion light years of uneven space, the universe becomes an accomplice in its transformation. What we call redshift is both motion and memory. It is the sum of every valley, every wall, every whisper of dark energy that light encountered along the way. Imagine a single photon leaving a distant galaxy on the edge of our void. For hundreds of millions of years, it drifts through the thin cosmic air. No stars, no dust, only the faint gravitational pull of faraway filaments. Its wavelength stretches with the expanding fabric around it, growing longer and redder. By the time it reaches Earth, entire civilizations could have risen and vanished. We capture it in a telescope, measure its color, and write down a number. That number becomes part of the data that defines the universe, and in that quiet moment of measurement, we forget that the photon's journey shaped the very truth we are trying to read. The geometry of emptiness bends reality in other ways too. Inside a void, time itself flows differently. Not because relativity ceases to hold, but because the metric of expansion subtly changes. Clocks in underdense regions tick a fraction faster than clocks in overdense ones. The effect is infinitesimal, far too small for human senses, yet on cosmic scales it matters. When we compare signals from different parts of the universe, those tiny discrepancies accumulate into measurable differences. The universe carries its own network of shifting time zones, defined not by rotation or orbit, but by the curvature of space. All these influences, on light, on time, on motion, converge in our instruments as the single quantity we call the Hubble constant. It is not that our telescopes are wrong, it is that the cosmos itself has texture, and texture resists simplification. We are trying to describe a rough surface with smooth numbers. The discovery of the KBC Void forces cosmologists to confront this texture. It invites them to model the universe not as a perfect average, but as a landscape, with hills, valleys, and rivers of expansion that flow at slightly different rates. In this view, the Hubble constant is not a universal truth, but a local dialect of cosmic motion. The early universe speaks one language, our neighborhood speaks another. For decades, cosmology has sought precision, more digits, smaller uncertainties, cleaner fits, yet sometimes what looks like noise is actually a new kind of signal. The discord between 67 and 73 kilometers per second per megaparsec may not be an error to fix, but a story to listen to. It may be the voice of the void itself. The beauty of science lies in its patience. When the data disagree, scientists do not despair. They map, simulate, and measure again, trusting that truth will emerge from persistence. Already, new surveys such as the Dark Energy Spectroscopic Instrument and the Euclid mission are charting millions of galaxies, peeling back the cosmic web in unprecedented detail. Their maps will test whether the KBC Void truly accounts for the Hubble tension or whether deeper physics waits beyond. Whatever the outcome, one lesson endures. Even emptiness has a structure, and that structure shapes everything we see. Light, traveling across that structure, becomes both messenger and sculptor. Through it, we glimpse not only the architecture of the universe, but also the quiet humility of our own position within it. We are not at the center of creation. We are at the center of a story told by light, density, and time, a story that began long before Earth existed and that will continue long after the last star fades. The night sky above us is not just a canvas of stars, it is the shadow of geometry itself. Every sparkle, every faint smear of distant galaxy is light that has survived the distortions of an imperfect universe to bring us news of what lies beyond the void. And perhaps, if we listen closely, we can hear the meaning hidden in its silence, that even in the deepest emptiness there is connection, that even where matter thins, truth still travels, and that our small blue world, floating in the quiet center of a billion-light-year hollow, is exactly where the universe chose to let awareness bloom. Before the void, there was light, and before the light, there was expansion so fierce that it silenced all memory of what came before. Cosmologists call it inflation, a fraction of a second when the universe grew from smaller than an atom to larger than a galaxy cluster. In that instant, quantum fluctuations, tiny random ripples in the energy field, were stretched to cosmic size. Those ripples became the blueprint for everything, galaxies, clusters, and the yawning gaps between them. From that inflationary seed grew contrast. Where density was slightly higher, gravity gathered matter and slowed expansion. Where it was lower, matter drifted away and expansion quickened. Over billions of years, this gentle imbalance sculpted the grand pattern we see today, the cosmic web. Its filaments shine with billions of galaxies. Its nodes are superclusters. Its cavities are the voids. We live inside one of those cavities, and our place within it is not coincidence, but consequence. To trace that history is to understand the three invisible forces that rule the universe's shape: dark matter, dark energy, and gravity. Dark matter is the quiet architect. It neither shines nor absorbs, but it has mass, and mass bends space. Without it, galaxies would tear themselves apart, clusters would never form. In the early universe, dark matter condensed first, forming invisible scaffolds where ordinary gas could later cool and ignite into stars. Even now, these halos of unseen matter define the geometry of every structure, from small galaxies to the sprawling filaments that lace across hundreds of millions of light years. In the deepest parts of a void, even dark matter is scarce. That scarcity weakens gravity's hold, allowing the local expansion to outrun the average. The result is a bubble where space itself stretches slightly faster than the cosmic mean, a feature, not a flaw, carved by the same physics that built everything else. Dark energy, on the other hand, is the universe's persistent whisper. It does not clump, it does not gather, it pushes. Roughly 7/10 of the universe's total energy lies in this form, a constant pressure that accelerates expansion on the largest scales. In dense regions, gravity resists it. In voids, it wins easily. That is why the KBC void, thin as it is, behaves like a magnifying glass for dark energy's influence. Here, acceleration is unmasked. Between these two unseen forces, gravity weaves the final pattern. It is the mediator, attractive yet democratic, responding only to mass. Gravity makes structure possible, but also defines emptiness by contrast. Where it piles up galaxies into clusters, it leaves behind vast regions of near silence. Every ridge of brightness owes its existence to a shadowed hollow nearby. If we could compress the story of the cosmos into a single human lifetime, inflation would be the first heartbeat, dark matter the bones, and dark energy the long breath that carries everything apart. The void would be the space between those breaths, the pause that gives rhythm meaning. Scientists have recreated this cosmic rhythm inside computers. Supercomputers simulate billions of particles interacting under the laws of gravity. And expansion. At first, the screen shows only fog. Then, slowly, tendrils appear, thin, bright threads connecting knots of mass, separating great dark basins. When the simulation is complete, it looks eerily familiar. The same filaments, the same hollows, the same overall foam-like texture that telescopes reveal in the real universe. From simplicity arises complexity. From randomness, pattern. But even in these digital universes, the precise shape of our own environment, a void as large as the KBC region, remains uncommon. Not impossible, just rare. Like finding a vast, calm lake in a landscape of rolling hills. That rarity is what makes our perspective both valuable and confusing. It is why our measurements of cosmic expansion differ from what the early universe predicts. We are observing from an edge case in the grand simulation. Inflation explains why the universe is so uniform overall, why across 90 billion light-years of visible space, the cosmic microwave background varies by less than 1 part in 100,000. Yet inflation also explains why small deviations persist. It amplified the quantum noise of the beginning into the structure we see today. Every filament, every cluster, every void began as a random fluctuation in a field that no longer exists. Even the KBC void, this enormous absence surrounding us, can trace its ancestry to a microscopic wrinkle in the fabric of the infant cosmos. That thought alone bends the mind. The emptiness between galaxies today is the fossil of quantum chance. 14 billion years ago, an almost invisible fluctuation grew into a region where matter never quite caught up. Now, billions of light years across, that ancient imperfection defines how we perceive the universe. The cosmic web continues to evolve. Gravity pulls the dense regions tighter, dark energy stretches the spaces wider. Voids expand, merge, and sometimes swallow smaller voids within them. They are the universe's slow exhalations. Each passing billion years leaves the web more distinct, clusters brightening, filaments thinning, voids deepening. Eventually, dark energy will dominate so completely that galaxies outside our local group will drift beyond the reach of light altogether. Future observers will look up and see only the faint islands that remain gravitationally bound to them. The grand architecture will fade into darkness, not because it disappears, but because it moves forever out of sight. To live now is to witness the universe at its most intricate, a moment when the web is still visible, when the voids have shape but not isolation. We inhabit the balance point between clustering and escape. It is a transient beauty, one that will not last, but one that allows minds like ours to exist and to wonder. The next time you see an image of the cosmic web, those glowing filaments in dark spaces, remember that it is not merely a picture of matter. It is a portrait of time. Each thread marks where gravity lingered. Each void marks where expansion outran it. Together, they form the map of the universe's memory. And somewhere within that map, A small spiral galaxy called the Milky Way drifts quietly in the half-light between density and emptiness, measuring the cosmos and dreaming about its own position in the whole. It is easy to think of a void as a place of nothingness, but it is also a cradle for understanding. Without contrast, pattern disappears. Without silence, sound loses meaning. The KBC Void, far from being a cosmic anomaly, may be the universe's way of reminding us that truth often hides in the spaces between events. Even here, surrounded by near nothing, physics continues unbroken. Dark matter still whispers through the vastness, dark energy still presses outward, gravity still links every atom of our being to every distant star. The void does not isolate us. It connects us by subtraction, showing what remains when all else is gone. Somewhere in the future, when our descendants look back across deeper maps of galaxies and measure expansion with greater precision, they may find that the story we tell today was only the first chapter. Perhaps the KBC Void will become one of many known hollows, its significance absorbed into a broader understanding. Or perhaps it will remain unique, a quiet reminder that even the most advanced model can overlook the influence of its own vantage point. For now, we live inside its slow, invisible breath, a billion light-year sphere of relative emptiness that teaches us the value of context. And as we listen to the echoes of the Big Bang and trace the faint paths of light through the darkness, we are learning that the universe is not a static stage, but a living, expanding story, one written equally in presence and in absence. The map of the universe is drawn in light. Every dot on that map is a galaxy, each one containing hundreds of billions of stars. But the true artistry of cosmology lies not in counting those lights, but in measuring the dark space between them. To measure emptiness, astronomers use the only tools the universe allows: distance and motion. Both are hidden in light's code, the way its color shifts, the way its brightness fades. From those clues, a grand three-dimensional picture emerges, fragile yet immense. The first great surveys of the modern age, 2DF, Sloan Digital Sky Survey, later the Dark Energy Survey, transformed our sense of scale. They did not simply photograph the sky, they measured redshifts for millions of galaxies, turning flat constellations into depth. For the first time, humanity saw the universe as structure: walls, filaments, knots, and the vast black basins between them. The image looked almost biological, like a neuron network glowing in the dark. That resemblance was no accident. Both follow the mathematics of growth, simple rules repeated until complexity appears inevitable. When scientists slice through those cosmic maps, they see patterns, repeating across scales. Clusters line up along threads tens of millions of light-years long. Voids open between them, sometimes merging into even greater caverns. Our own region, home to the local group, the Virgo cluster, and beyond that the Laniakea supercluster, sits in a gently sloping depression of that network. Farther out, the galaxy counts rise again. That slow gradient is the fingerprint of the KBC Void. To chart it, researchers count galaxies within concentric shells around us. The result is unmistakable: a steady deficit extending hundreds of millions of light-years in every direction before density climbs back toward the cosmic average. From those counts alone, the KBC Void reveals itself like the faint outline of a valley at dawn. Redshift surveys make the picture dynamic. Each galaxy's color tells how fast it moves away. Plot those velocities against distance, and patterns of flow appear. Near the centers of voids, galaxies stream outward. Near filaments, they slow and turn inward. Our measurements fit that script precisely. We are drifting outward, part of the slow exhalation of an underdense cosmos. Even the microwave background, the oldest light, confirms it indirectly. Its slight dipole, the minute difference in temperature across the sky, encodes our motion through space. When scientists remove the known pull of nearby clusters, a residual drift remains, consistent with being nudged from the center of a large void. Different instruments, different wavelengths, all whisper the same conclusion. Modern technology turns those whispers into song. The Dark Energy Spectroscopic Instrument, mounted on a telescope in the Arizona desert, is cataloging tens of millions of galaxies with machine precision. The Euclid Space Telescope, orbiting far above Earth's atmosphere, is mapping the sky with a clarity no ground-based instrument can match. Together they are weaving a map so detailed that the outlines of voids and filaments emerge automatically from data, no human tracing needed. The universe is sketching its own portrait. Inside laboratories, supercomputers compare those portraits with synthetic universes grown from theory. By adjusting parameters, matter density, dark energy strength, the initial seeds of fluctuation, scientists create digital skies and test whether any reproduce our observed patterns. Most simulations generate voids, but few grow one as broad as the KBC region. When one does, the same effect appears. Local expansion rises, mimicking the Hubble tension. The coincidence grows harder to dismiss. To confirm such an enormous structure, astronomers use every independent yardstick they have. Baryon acoustic oscillations, the frozen ripples of primordial sound waves, mark a standard distance scale across the cosmos. Supernovae provide standard candles, bright enough to measure far beyond our local cluster. Each technique gives a slightly different answer for the Hubble constant, but when corrected for the underdensity implied by the KBC void, those values begin to converge. The puzzle pieces align as if the void itself were the missing border. Precision now depends on subtle corrections. A single supernova miscalibrated, a small patch of dust unaccounted for, can shift the result. But with thousands of data points, the pattern persists. The higher local rate of expansion fades smoothly toward the lower cosmic value at greater distances. The gradient is the map. The void is real. There's a quiet beauty in this detective work. No experiment can leave the laboratory of our location. We measure from one fixed coordinate in space and must infer the rest. That limitation could breed frustration, but instead, it breeds creativity. To compensate, scientists layer evidence like transparent sheets until an image emerges through overlap. Each dataset, each instrument adds color to the same invisible shape. Slowly, the KBC void ceases to be theory and becomes geography. And yet, mapping it also deepens the philosophical unease. If our local measurements differ because of environment, then the universe is not perfectly democratic. It still obeys the same laws everywhere, but those laws play out on uneven terrain. Homogeneity was never a guarantee. It was an approximation. The deeper lesson lies in method. Science must now fold geography into cosmology. Every future measurement of expansion, every study of dark energy, must correct for local structure. To ignore it would be to mistake the shape of our valley for the shape of the whole landscape. Already, new statistical techniques treat the universe as a nested hierarchy. Voids within voids, filaments feeding clusters, clusters surrounding hollows. This cosmic web reconstruction allows models to subtract local effects before comparing to the early universe. In that process, the Hubble tension may soften until the two expansion rates meet like the closing of a seam. If that happens, the void will not only explain a mystery, it will have restored coherence to the story of creation. The tools that make this possible are monuments of collaboration, instruments on mountaintops linked to satellites in orbit, pipelines of data flowing through supercomputers that never sleep. They embody a truth opposite of the emptiness they study. That meaning is built together. In the long nights at observatories, astronomers watch the faint red smudge of a distant galaxy drift across the sensor. They know that each exposure adds another stitch to the universe's tapestry. Between the quiet clicks of the shutter, they think about distance, about time, about the gentle irony that we measure vastness by catching its smallest messengers. Every photon is a witness, every measurement is an act of faith in reason. One day, the maps will be complete enough to show not only where matter is, but where we are within the balance of void and wall. Then, humanity will know its position with the same certainty sailors once knew, their latitude under the stars. Perhaps on that day we will finally accept the simple truth that has been waiting since the first galaxies formed. We are not in the middle of everything, but we are in the middle of our own story. And that is enough. The hardest discoveries are not the ones that change equations, they are the ones that change perspective. For centuries we have repeated a comforting idea that no place is special. From Copernicus to Galileo, from Einstein to today, every advance in astronomy has pushed us further from the center. Each step felt like loss, yet each revealed a larger truth. Now the void asks us to take one more step, to accept that even our measurements of the universe's speed are tinted by where we stand. When astronomers first proposed that we might live in a giant underdensity, the reaction was quiet disbelief. It sounded too convenient, almost egocentric in reverse. Surely the cosmos would not place us in such an improbable location, just as our instruments grew sensitive enough to notice. But the numbers refused to yield, and disbelief slowly turned to curiosity. Conferences filled with debates about coincidence and probability. Statisticians calculated the odds of a void this size forming by chance. Philosophers wrote essays about observation and bias. At the edge of those discussions hovered a deeper unease. If our cosmic neighborhood shapes our data, then knowledge itself becomes local. There is no absolute vantage point, only perspectives stitched together by dialogue. For some scientists, that idea is thrilling. It makes cosmology less like divine revelation and more like a conversation with the universe. Every measurement becomes a question, every anomaly an answer in disguise. Others find it unsettling. They long for a view from nowhere, a single objective truth unmarred by geography. The void whispers that such purity may not exist. Yet even discomfort can be productive. It keeps humility alive. To admit that our instruments are biased by our cosmic address is not to surrender accuracy. It is to refine it. Science grows sharper when it includes its own shadow in the calculation. In long observatory nights, you can see that humility at work. Teams scattered across continents share data through quiet networks of light. A telescope in Chile maps galaxies the human eye will never see. Another in Hawaii measures the spectra of distant supernovae. In an office somewhere, a graduate student adjusts parameters, chasing decimals across the screen. Together they build a mosaic so immense that no single person can hold it all in mind. That, too, is part of the lesson. Knowledge now requires community the way stars require gravity. Outside the laboratories, the idea of living in a cosmic desert carries a strange poetry. People imagine loneliness, but scientists feel gratitude. Without emptiness, there would be no clarity. Without contrast, no pattern. The KBC Void is not exile, but opportunity. Oh, vantage point clean enough to test the limits of theory. It is as if the universe, in its quiet way, cleared a window for us to look through. Some nights, when the data load slows and silence settles over the observatory control room, someone inevitably glances up at the real sky. It is never as dark as one expects. The Milky Way drapes across it like a faint river of dust. To think that all of that light floats inside a greater darkness is both humbling and comforting. The cosmos does not need our belief to be beautiful. In the coming years, as new telescopes launch and new maps emerge, the picture will sharpen. Perhaps the void will shrink under better measurements, or perhaps it will expand, confirming our peculiar home. Either way, the discovery will remind us that truth evolves with detail. The universe is patient. It allows us to revise our understanding again and again. And if, in the end, we remain creatures of a cosmic valley, then so be it. We will measure from our hollow and learn what emptiness can teach. For emptiness, it turns out, is not the opposite of existence. It is the space that lets existence be known. When future generations read the data we gather now, they will not see pride or certainty. They will see curiosity written across 1 billion light-years of sky. They will see a species that dared to map the invisible, to admit its biases, and still to search for order. Perhaps that will be our truest legacy, not the numbers themselves, but the courage to keep refining them. And maybe, just maybe, the universe will smile, if such a thing can be said of the infinite, at the thought that one small world inside a vast void tried so hard to understand why the stars drifted faster than they should. Time does not pass the same everywhere. That truth, whispered by Einstein more than a century ago, stretches far beyond the pull of planets or the spin of stars. In the great architecture of the cosmos, even emptiness has its own tempo. Inside a void, where gravity is weak and space expands freely, clocks tick a little faster. In the crowded hearts of clusters where matter bends space deeply, time runs slightly slow. The difference is invisible to human eyes, yet written into the rhythm of light itself. Photons traveling from dense walls into our underdense valley arrive ever so slightly blue-shifted, their wave crests squeezed by the faster beat of our local spacetime. To measure it requires precision bordering on obsession, atomic clocks tuned to the heartbeat of the universe. But it is there, a quiet syncopation between fullness and emptiness, a cosmic music of delay and haste. The void is not only a place, it is a pace. Galaxies inside it evolve differently too. Where clusters are crowded arenas of collision and cannibalism, the void's isolation breeds gentleness. Dwarf galaxies drift for billions of years without encountering neighbors. Their stars form slowly from vast reserves of cold hydrogen. No tidal forces twist them into spirals. No mergers ignite furious bursts of light. They grow in solitude, small and undisturbed, living fossils of the early cosmos. Astronomers who study these faint systems find that they retain the chemical simplicity of youth. Their stars are metal poor, their histories unhurried. Each one is a memory preserved in low density, a diary written in starlight about a calmer universe that existed long before clusters grew violent. In that way, the KBC Void is both present and past. It allows galaxies like ours to glimpse the conditions of an earlier era. Our own Milky Way, though not a true void galaxy, still feels the influence of the surrounding emptiness. Its motion, its neighbors, even the shape of the local group's expansion are molded by the soft outward pull of the underdensity. The void is the stage beneath every orbit. When cosmologists simulate the far future, they see what this means. Dark energy, constant and relentless, will keep stretching space. Galaxies in the dense filaments will cling together, bound by gravity, but everything else will recede beyond reach. Voids will grow wider. Their walls will thin until each cluster becomes an island adrift in a sea of nothing. In time, 100 billion years or more, even those clusters will vanish from view, their light redshifted beyond all detection. For future astronomers, if any remain, the universe will appear almost empty. The cosmic web will dissolve into solitude. Only the ghosts of local stars will glow against a horizon of silence. The clues that told us of the Big Bang, of expansion, of other galaxies, will fade into invisibility. Cosmic history itself will become unknowable. To us, living now, that thought feels tragic, but perhaps it is also merciful. The universe hides its beginnings as it hides its end, giving each epoch its own horizon of understanding. We, by chance and timing, exist at the moment when the evidence still fills the sky, when the void has formed but not yet consumed. We are witnesses positioned perfectly between creation and forgetting. In the vast mathematics of eternity, that coincidence is staggering. For billions of years, the universe was too chaotic to map. For billions more, it will be too empty to study. But in this narrow window, these few billion years around the age of 13 and a half, conditions align so that curious minds on a small planet can look outward and see the pattern entire. The cosmic web, the filaments, the voids, the acceleration, all visible, all measurable. We arrived at the right time and the right place to learn that we live inside a desert of light. That realization carries a gentle paradox. The void, which seems to represent isolation, is what allows us to understand connection. Because space is thin here, our view is clearer. Because gravity is weak, the motions of galaxies are purer signals of expansion. Our emptiness gives us sight. It is a window, not a wall. In dense clusters, light is trapped by gravity, bent and muddied by intervening mass. In our region, light travels almost untouched, That clarity lets us measure distances with unmatched precision, trace the cosmic microwave background without heavy distortion, and test dark energy in its cleanest form. The KBC Void, far from hindering observation, is a natural observatory carved by the universe itself. It is as though creation hollowed out a chamber so that awareness could echo inside it. When one sees the sky this way, the Hubble tension becomes not a crisis but a signpost. It reminds us that our measurements are alive, responsive to place, sensitive to perspective. To correct for our void is not to admit defeat, it is to acknowledge participation. We are part of the experiment we describe. The poet in every scientist feels that truth even when the data speak in decimals. The universe is not indifferent to our gaze, it shapes what we see through its own unevenness. Every photon that enters a telescope carries both message and filter, both fact and feeling of its journey through expanding space. And we, at the end of that journey, translate it back into knowledge, turning the texture of emptiness into understanding. As ages pass, the void around us will keep swelling. Galaxies now on the horizon will drift away until their light no longer reaches us. Stars will age, burn, and fade. But even then, in that distant future, the signature of our hollow will remain embedded in the fabric of space, a gentle scar left by difference, a memory of imbalance written in the coordinates of eternity. Perhaps some far descendant, orbiting a lonely star in the far-off remnant of the Milky Way, will point a telescope toward the dark and measure the faint curvature of local space-time. They will find the same pattern we see now, an expansion slightly faster than expected, an underdensity surrounding them. They will conclude, as we have, that they live in a void, and they will be right. Because the void is not a temporary feature, it is a natural stage in the universe's long breathing. It will persist even as stars die and matter thins, a quiet rhythm beneath all becoming. To live inside that rhythm is not a curse, it is privilege. It means that for a brief window of cosmic time, the universe allowed itself to be known through us, and we, in return, gave it language, expansion, dark matter, Hubble constant, KBC void. These are our human names for a truth that does not need words, but welcomes them nonetheless. The void does not erase us, it frames us. Like silence around a note, it gives meaning to the sound, and the sound, faint but real, is our curiosity echoing through the dark, proof that even in the most rarefied places, thought can take root. The future of discovery begins, as always, with a mirror pointed toward the night. New mirrors are rising everywhere, in deserts, on mountain peaks, drifting through orbit, poised above the blur of our atmosphere. They are patient, eyes built to read the faintest handwriting of the universe. Those pale red lines where galaxies hide their motion and time itself leaves fingerprints. Each new instrument extends our reach by fractions of a percent, but those fractions are everything. Precision is how humanity slowly negotiates with infinity. The James Webb Space Telescope already listens to the earliest galaxies, measuring how their light has stretched across 13 billion years of expansion. Euclid, sailing silently at the second Lagrange point, is tracing how matter and dark energy compete for control of the cosmic web. On Earth, the Vera Rubin Observatory prepares to photograph the entire southern sky every few nights, capturing billions of transient flashes, supernovae, quasars, variable stars, each a new ruler for distance. And in the quiet of Arizona, the dark energy spectroscopic instrument gathers redshifts by the millions, threading them into a three-dimensional map so vast that no human could ever look at it all at once. Together, these projects form a single experiment, a conversation between light and gravity. They will test whether the local underdensity we call the KBC Void truly accounts for our inflated Hubble constant, or whether something deeper, something woven into the laws of physics, still hides beneath the data. If the void explanation holds, the tension will ease. The two expansion rates, local and cosmic, will converge after correction, and the universe will feel whole again. The standard model will remain intact, elegant, and unbroken, its parameters adjusted, but its foundation firm. Dark energy will stay constant, general relativity will keep its crown. We will have learned that perspective matters, that even the most universal truths are colored by geography. But if the gap persists, if after every correction, every recalibration, the numbers refuse to meet, then the void will have led us to a deeper frontier. We may find that dark energy changes over time, or that new particles once hummed through the early cosmos, altering its growth. We may discover that gravity itself, so faithful within solar systems, drifts slightly from Einstein's prescription when stretched across billions of light years. Each possibility is both thrilling and terrifying, for it would mean that the universe is stranger than even our boldest equations allow. Astronomers prepare for both outcomes with the same humility. They know that the sky often answers one question by asking three more. The goal is not closure, but refinement, the quiet satisfaction of seeing uncertainty shrink by a measurable fraction. That is the rhythm of science, a heartbeat made of patience. Still, there is an undercurrent of emotion in this quest. When you spend your life chasing decimals through the void, you begin to feel affection for the very mysteries that resist you. The Hubble tension, once framed as a crisis, has become a companion, an unsolved chord that keeps cosmology alive and listening. In the control rooms of observatories, data scrolls across monitors like rainfall. Spectra appear, peaks shift, algorithms hum. Somewhere in those endless columns of numbers lies the next correction, the next revelation. The air smells faintly of ozone and coffee. Outside, wind brushes the domes. Above them, photons that left their galaxies before Earth existed are striking metal and silicon, turning cosmic silence into information. To anyone who has stood under such a sky, the feeling is unmistakable, awe mixed with responsibility. We are the only species we know of that measures the universe from inside it. We do not command the cosmos, we decode it, bit by bit, humility by humility. If the coming decade of observation confirms that we live in a giant underdensity, then textbooks will change, but the wonder will remain. Students will learn that even the cosmic expansion is local in flavor, that context shapes every constant. And perhaps they will sense the deeper metaphor, that perspective, whether cosmic or human, always matters. Because the void is not only a structure of space, it is a mirror of thought. It shows us that knowledge, too, expands unevenly, that understanding accelerates where curiosity is light and slows where it is dense with assumption. The new generation of telescopes will finish their surveys, new theories will rise and fall. But the larger story will continue. The story of consciousness pushing against the boundary of what can be known, using light itself as a ladder. Someday, centuries from now, when these instruments are relics and the stars themselves have changed, someone will still look up and ask the same question we asked tonight. How fast does the universe expand? And hidden inside that question will be another. How fast can understanding grow? The answer will come, as always, in silence first, then in light. When you gaze into the night, you are looking outward in space and backward in time. Every shimmer is an ancient memory, a fragment of what once was. Between those fragments lies the greater truth, the silent distance that holds them apart. That distance is not emptiness, it is the medium of everything. The void teaches this quietly. It shows that absence is not the enemy of being, but its balance. Where galaxies cluster, gravity sings loudly. Where the void stretches, the melody pauses so we can hear the echo. Without the pause, the song would be noise. For generations, humanity feared nothingness. We filled our myths with light to drive back the dark. Yet science, with the patience of centuries, discovered that the dark itself is fertile. Stars are born from it, galaxies evolve within it, and consciousness, our brief spark, emerges to notice it. To live in a void is not to be exiled from meaning, it is to stand at the still center of it. Think of what that means for our species. We began in caves, telling stories about lights in the sky. Now, with instruments that catch single photons, we have mapped the architecture of creation, and just as we grew certain of our insignificance, the universe whispered a paradox. You are small, yes, but your smallness allows precision. From within a desert of 1 billion light years, one mind can measure the breadth of the cosmos. The void reframes humility. It is not humiliation, but awareness of scale. To know that we inhabit a thin bubble of underdensity is to realize that our perspective is both limited and precious. We see from one valley, yet that valley offers a clear horizon. Clarity is born of distance, meaning is born of context. Philosophers call this the cosmological principle. No place is special. But the void adds a footnote. Every place is special to those who observe from it. Objectivity is not the absence of position, it is the recognition of it. The universe does not flatten individuality, it multiplies it. Each vantage point is another angle of truth. If a civilization far away lives inside a dense cluster, their night sky would blaze with 10,000 suns. Their measurements would differ, their myths would differ. To them, the cosmos might seem slower, heavier, more crowded with fate. From our hollow, the universe feels light, transparent, full of room to wonder. Both perspectives are real. Together, they form the whole. In this way, the void becomes a metaphor for coexistence. It reminds us that disagreement in data is not failure, but dialogue. The Hubble tension, frustrating as it seems, is the cosmos inviting us to listen more carefully, to compare notes between emptiness and abundance. Science thrives on that tension, just as music thrives on dissonance that resolves into harmony. And when we finally reconcile those measures, when the local and the cosmic expansion merge into one coherent picture, it will not erase the void's lesson. It will confirm it. It will show that truth is mosaic, assembled from pieces that at first do not fit. There is a spiritual quiet in that realization, not the quiet of surrender, but of understanding. The same physical laws that govern galaxies also govern thought. Both expand when released from confinement. In the space between certainty and doubt lies creation. Look again at the night sky. The faint band of the Milky Way curves like a bridge over your head. Each star you see is moving, every photon slightly red-shifted by the universe's breath. You are watching motion so vast that your own heartbeat becomes the metronome of eternity. And yet you feel it. The pulse of distance, the rhythm of being small and aware. To live inside a cosmic void is to live inside perspective itself. It is to recognize that our world, our history, our science are all brief notes in a longer composition whose composer is chance and whose theme is continuity. We are the moment when the universe looked back at its own vastness and called it beautiful. The emptiness around us is not loneliness. It is room to think. In that room, curiosity grows. Science breathes, art dreams. And as long as light continues to travel, meaning will travel with it. Perhaps that is the ultimate correction to the equations, the one beyond mathematics, that in all this space, something learned to ask why, and in asking, filled the void with voice. There comes a point after all the data and the diagrams when science becomes silence again. The telescopes shut their domes, the instruments cool, and the sky above them returns to what it has always been, endless, patient, aware only of its own expansion. And in that silence, a thought arises. Perhaps discovery is not about conquering mystery, but about learning to live with it. The KBC Void will outlast every observatory on Earth. It will remain, growing larger as dark energy pushes its boundaries outward until even the nearest filaments drift beyond the reach of light. One day, long after humanity's name has faded, the void will still be here, empty, perfect, expanding into its own echo. And that thought, strange as it sounds, carries comfort, because it means we were part of something enduring, something grand enough to continue without us. We were the witnesses who noticed the hollow. We gave it a name. We measured its breadth and learned that space itself is alive with subtlety. We realized that emptiness can shape the universe as surely as matter does, that even nothing has structure. Every photon that ever crossed this valley carries our signature now, however faint. The instruments we built, the ideas we formed, changed the way the cosmos is known, and knowledge, once created, is never entirely lost. It ripples outward just like light, slowing, redshifting, fading, but never stopping. When the last astronomer looks up and the sky holds only the afterglow of nearby stars, they will still be part of this lineage of asking. To question the dark is to belong to the universe. To listen for its answer is to realize that the answer is already within the listening. Maybe that was the purpose of the void all along, not an accident, not an emptiness, but a space wide enough for awareness to unfold, a silence so vast that thought could find room to grow. In a denser cosmos, perhaps there would be no observers at all, only collisions, noise, and heat. But here, inside this desert of distance, life had time to wonder. The Hubble tension, the measurements, the debates, all of it becomes one continuous gesture, the universe learning to measure itself through us. We are its equation and its experiment, its question and its tool. When we call it expansion, it calls us curiosity. The two are the same motion, reflected across scale. Think of the chain, from the first atoms condensing out of cooling fire, to stars, to planets, to minds that can name the fire. Think of the improbability of it, the grace. Out of the smallest fluctuations in quantum foam came galaxies, voids, and eventually a consciousness that asked, "Why are we here?" And the answer, whispered by the background. Radiation is simply because here exists. Our void is not a flaw, it is a canvas. We are not off-center, we are precisely where perspective could bloom. We do not live in isolation, but in clarity. When you stand beneath the night and feel the thin wind of time passing over your skin, remember that you are standing at the center of a billion light-year silence, and that silence is listening back. It holds your pulse as gently as it holds the drift of galaxies. Every breath you take is part of the same expansion that moves the stars apart. The cosmos is not cold, it is careful. It gives space for everything to happen. It gives space for you. Perhaps, after all the mathematics, that is the final constant. The universe is generous with room. So let it expand. Let the void grow deeper, and the filaments stretch thinner, and the light take longer to arrive. We have seen enough to know that even in the vastest emptiness, something stirs, something counts, something dreams. We are that dream, briefly awake inside infinity. And when our small flame fades, the echo of our curiosity will remain, woven into the background glow, written in the faint warmth between the galaxies, carried forever through the quiet heart of the cosmic desert.